welcome to the Sleepy Club. I'm really glad you're here. Tonight, we'll be drifting gently through the sky above us, exploring the quiet science behind weather, the soft movement of the air, distant clouds slowly building, snow falling in careful silence, and warm afternoons shaped by sunlight and time. Think of this as a slow floating journey through the atmosphere, all while you remain comfortable, safe and relaxed where you are. This is a place where we learn while we rest, where curiosity moves softly, and knowledge arrives without urgency. So as you listen, allow your breathing to slow, your body to grow heavier, and your thoughts to lose their sharp edges. Now a small and friendly warning. This video is meant to help you unwind, but there's always the chance that something might catch your interest just enough to keep you listening. And if you find yourself awake late at night, quietly wondering about towering storm clouds or the invisible forces that guide the wind, at least your mind will be resting in a thoughtful way. Take a moment to notice where you are in the world right now, what time it is, whether the sky outside your window is dark, pale, or just beginning to change. You're very welcome here. If you enjoy calm, curiosity-filled journeys like this one, consider liking the video and subscribing to the Sleepy Club. It helps these quiet stories reach others who need a peaceful place to land. So now, make yourself comfortable. Let your shoulders drop. Take a slow breath in and let it ease out naturally. And when you're ready, we'll begin our unhurried journey into the calm and fascinating world of weather. Tonight we are going to explore how weather works and the science behind every raindrop rainbow and rumble in the sky. We begin by noticing something that surrounds us at all times, yet is often overlooked unless it starts to misbehave, which is the air. We live at the bottom of an invisible ocean of gases, a vast, gently moving sea called the atmosphere. Unlike the ocean of water, we do not need special equipment to breathe here, though. It can sometimes send hair drifting and papers sliding away. The atmosphere is the stage on which all weather unfolds. In proportion, it is about as thin as the skin of an apple, and most of it clings close to the earth in a shallow band. When an airplane cruises high above the ground, much of this ocean has already been left below. The atmosphere is arranged in layers, each with its own character, like levels in a cake, though far less edible. The lowest layer, where all familiar weather occurs, is the troposphere. This is where clouds form rainfalls and winds stir. The troposphere reaches several miles upward on average, growing taller near the equator and shorter near the poles. Above it lies the stratosphere, home to the ozone layer, which acts like protective eyewear shielding the planet from harsher sunlight. Higher still is the mesosphere, where meteors burn into bright streaks. Beyond that stretches the thermosphere, a realm of auroras and satellites where temperatures can rise extremely high, yet would not feel hot because the air is so thin. At the outer edge, blending into space, is the exosphere, a faint whisper of atmosphere, where molecules drift far apart and slowly escape into the cosmos. For now, we remain comfortably within the troposphere, our home layer. The air here is made mostly of nitrogen, with oxygen close behind, and the rest made of trace gases, such as argon, carbon dioxide, and varying amounts of water vapor. It may not sound glamorous, but this mixture is ideal for life on Earth. To understand weather, we must watch how air behaves, because air moves like a fluid. It flows, swirls, and tumbles, and responds strongly to changes in temperature and pressure. Warm air rises because it is less dense, while cold air sinks because it is heavier. This simple pattern of rising warmth and sinking coolness is the steady pulse of weather. The sun does not heat the earth evenly, with more energy reaching the equator and far less reaching the poles. Land warms faster than water, and valleys are often warmer than mountains. These contrasts create pockets of warm and cold air, and the atmosphere continually works to smooth out these differences. When sunlight warms a patch of ground, the air above it begins to rise, and as it rises, it cools. Cooler air cannot hold as much moisture, so water vapor condenses into tiny droplets that form clouds. Surrounding cooler air then flows in to replace the rising air, and this motion is called convection. The same process stirs soup in a pot or cooks food evenly, but on a planetary scale. Air also has weight, and the pressure from all the air above us presses gently downward at all times. This pressure changes with height and with weather patterns. High-pressure systems tend to be calm with sinking air that discourages cloud formation. Low-pressure systems are more active with rising air that encourages clouds, rain, and storms. Wind is created as air moves from areas of higher pressure toward areas of lower pressure, seeking balance. Because the Earth rotates rapidly, this moving air is deflected in a pattern known as the Coriolis effect. In the northern half of the planet, winds curve to the right, and in the southern half, they curve to the left. Add moisture and shape and the cycle of day and night, the atmosphere is in constant motion. Even on a clear, calm day, invisible currents slide past gentle shifts in humidity and temperature, unfolding quietly. The atmosphere is always changing, always flowing, and never exactly the same twice. What makes it elegant is that this immense system runs without control or command, guided only by physics, gravity, and the simple truth that energy spreads out. Heat moves from warm places to cool ones, and pressure always seeks balance. Water is always seeking to change its state as it rises unseen into the air, then gathers itself and falls back to the ground, only to begin the journey again. The atmosphere, too, is always reaching for balance. It rarely finds it, and yet it never stops trying. This endless attempt is the reason weather exists. Earth is a restless world, wrapped in warm gases, turning slowly in sunlight and moving through space. Every breeze, every drifting cloud, every falling raindrop is part of this unbroken search for equilibrium. When you look up and watch clouds slide across the sky, or feel wind brush past your face, those motions are not random. They are part of something vast, ancient, and quietly beautiful. An invisible ballet guided by sunlight and shaped by gravity. And it all begins in the air that surrounds and sustains us. The sun, though unimaginably distant, is the true conductor of Earth weather. Without it, the planet would be a frozen silent stone with no wind, no clouds, and no forecasts warning us of sudden rain. Solar energy is the primary engine behind all weather. It reaches Earth as sunlight, a form of electromagnetic radiation, and warms the surface of the planet. The atmosphere itself is not heated directly by the sun. Instead, the land, oceans, and everything resting on the surface absorb sunlight, and then release that warmth upward. The air is warmed from below, much like the air above a stove after it has been turned on. Because of the Earth's shape and its gentle tilt, sunlight does not strike all regions equally. The equator receives more direct energy, while the poles receive far less. This creates a persistent imbalance, where tropical regions warm quickly and polar regions remain cool. Wide. Nature responds to imbalance with motion. Warm air near the equator rises, lowering surface pressure. Air from surrounding higher pressure areas flows in to replace it. The rising air travels upward and outward toward higher latitudes, cooling along the way. Eventually, it sinks and moves back toward the equator near the surface, completing a vast looping pattern. Outdoor, this process forms large-scale circulation known as convection. Because Earth is large and wonderfully complex, this circulation does not occur in a single loop. Instead, there are three main convection cells in each hemisphere. Closest to the equator is the Hadley cell, which drives much of the tropical climate. In the middle latitudes lies the Ferrel cell, shaping temperate weather. Near the poles, the polar cell circulates cold, dense air. Together, these systems move heat from the equator to the poles, acting like a planetary conveyor belt. Within them arise the major wind patterns of the world. Near the equator, steady trade winds blow from east to west and have carried sailors across oceans for centuries, often without intending to explore new lands. In the mid-latitudes, westerly winds move weather systems from west to east, shaping storms and skies across continents. Near the poles, cold, dry, easterly winds circle the top and bottom of the world. These winds would flow straight if the planet were still, but Earth is always spinning. This rotation gently bends the paths of moving air in a phenomenon known as the Coriolis effect. It is not magic or intention, but physics quietly at work, guiding the motion of the atmosphere across a turning world. Imagine the Earth turning fastest at the equator and more slowly as you travel toward the poles. When air moves from one latitude to another, it carries with it the speed of rotation from where it began. This difference creates a gentle deflection as the air adjusts to its new surroundings. In the northern hemisphere, that deflection bends motion to the right. In the southern hemisphere, it bends to the left. This effect, known as the Coriolis effect, does not cause air to swirl wildly or dramatically. It works quietly and steadily over long distances and long stretches of time. Because of it, large storms rotate in opposite directions, in opposite hemispheres. It is why cyclones spin counterclockwise in the north and clockwise in the south. It is also why global wind patterns organize themselves into broad, graceful bands rather than dissolving into chaos. High above this slow bending motion lies another powerful influence shaping weather across the world: the jet stream. Jet streams are narrow, fast-moving rivers of air flowing high in the atmosphere along the boundaries between warm and cold air masses. The most familiar is the polar jet stream, which flows between cold polar air and the warmer air of the mid-latitudes. It usually travels several miles above the ground and can reach astonishing speeds far faster than any car on a highway. Jet streams form where sharp temperature differences exist, and they act like invisible guides steering storms and weather systems across continents. When the jet stream dips southward, it can pull cold air with it. When it arches northward, it can allow warmth to surge ahead. These shifts can bring heat waves, cold snaps, and powerful storms, and they often determine whether weather forecasts feel effortless or deeply uncertain. Jet streams even influence air travel. Flights heading east often move more quickly as they ride these high-speed winds, while westbound journeys feel longer as planes push against them. Beyond spinning winds and fast-moving air, the Earth itself is gently tilted on its axis. This tilt, slightly more than 23 degrees, is what gives rise to the seasons. As the planet circles the sun, different regions receive different amounts of sunlight throughout the year. When the northern hemisphere tilts toward the sun, it experiences summer with longer days and more direct sunlight. At the same time, the southern hemisphere tilts away and enters winter. Half a year later, the pattern reverses, and during the transitions of spring and autumn, both hemispheres receive similar amounts of solar energy. These changes reshape global temperature patterns and influence winds, storms, and ocean behavior. Covering most of the planet, the oceans play a central role in this system. They absorb immense amounts of solar energy and store it, slowly releasing warmth over time. Water heats and cools more gradually than land, which is why coastal regions tend to experience mild climates. But oceans are not still. Vast currents move through them, carrying warm and cold water across enormous distances. Currents such as the Gulf Stream transport warmth toward cooler regions, helping regulate climate far from the equator. When ocean patterns shift significantly during events like El Niño or La Niña, the effects can echo across the globe, altering rainfall, temperature, and drought patterns. So as you rest comfortably, you can picture the full choreography unfolding above and around you. Uneven sunlight warms the planet. Air rises and sinks in response. Earth rotation bends its path into curves. Jet streams carry weather swiftly across the sky. Ocean water store and release heat in slow, powerful rhythms. The result is a planet where no 2 days are ever identical. The breeze against your skin, the clouds drifting overhead, and the rain tapping softly on a window are all expressions of this immense system, a planetary ballet guided by sunlight, shaped by motion, and sustained in delicate balance for billions of years. All of it, from the gentlest breeze to the fiercest storm, begins with the distant warmth of the sun reaching out across space. Moisture in the air is something rarely noticed until it tangles hair or clouds glass. Yet this invisible presence quietly shapes weather everywhere. Water drifting unseen through the atmosphere forms clouds, brings rain and snow, and feeds powerful storms, while also painting the sky with some of its most breathtaking scenes. Moisture is the atmosphere hidden ingredient, and it is present even when the sky appears perfectly clear. Humidity is simply the name we give to water vapor suspended in the air. Water vapor is water in its gaseous form, and the amount the air can hold depends on temperature. Warm air is able to carry more water vapor, while cold air can hold far less air. This is why summer days often feel heavy and damp, while winter air feels sharp and dry. The difference is real, not imagined, because cold air truly contains less moisture. Meteorologists describe humidity in two ways: absolute humidity and relative humidity. Absolute humidity is the straightforward measure of how much water vapor is actually present in the air. Relative humidity is a comparison, a percentage showing how close the air is to being full at a given temperature. When relative humidity reaches 100%, the air is saturated and unable to hold more moisture. At that point, condensation begins and dew fog or clouds appear to wane. Even before saturation, high relative humidity can make the air feel sluggish because sweat evaporates more slowly, which limits the body's ability to cool itself. Dry air allows sweat to evaporate quickly, creating a cooler sensation, even if it feels stark and arid. Clouds may appear soft and weightless, but they are made of vast numbers of microscopic water droplets, or ice crystals depending on temperature. Each droplet is so small that it takes roughly 1 million of them to form a single raindrop. Despite their gentle appearance, clouds can be astonishingly heavy. A large, puffy cumulus cloud can weigh hundreds of thousands of pounds, comparable to a massive aircraft suspended overhead. Clouds form through a process that begins with evaporation. Water from oceans, lakes, rivers, and damp ground absorbs solar energy and becomes water vapor. This vapor rises with warm, buoyant air into the atmosphere. As it ascends, air pressure decreases, causing the air to expand and cool. Cooler air cannot hold as much water vapor, so the excess condenses into tiny droplets, or ice crystals. These droplets gather around microscopic particles such as dust salt or pollen known as cloud condensation. Nuclei particles. These tiny seeds allow moisture to collect and become visible. The shape and type of cloud that forms depends on how air rises and how much moisture it contains. When air lifts slowly and steadily, it creates stratus clouds, flat gray layers, that often blanket the sky and bring overcast calm. When air rises more quickly, it produces cumulus clouds, bright and billowing like floating towers. In unstable and very moist conditions, these clouds can grow upward into towering cumulonimbus formations. These giants dominate the sky and serve as the powerful engines behind thunderstorms. There are many other kinds of clouds drifting through the sky, each with a form and purpose of its own. Cirrus clouds appear high above the ground, thin and wispy, made mostly of ice crystals and often shaped like feathers. They frequently signal that a change in weather is approaching. Lenticular clouds form over mountains and hold smooth, rounded shapes that resemble hovering discs. Mammatus clouds hang downward in pouch-like forms and often accompany intense and dramatic weather. There is even a cloud type known as altocumulus castellanus, which looks like a line of small towers rising side by side across the sky. Their names may sound playful or fantastical, but they belong to a precise and very real scientific language. When a cloud forms, it does not always release rain immediately. The tiny droplets inside must grow large enough to overcome air resistance. This growth happens through coalescence as droplets collide and merge into larger drops. Once they become heavy enough, they begin to fall toward the ground as rain. In colder clouds, this process may involve ice crystals instead, as moisture freezes around them and builds mass until snow falls. Raindrops themselves are not shaped like tears as often imagined. As they fall, they flatten along the bottom due to air resistance, and if they grow too large, they can split apart into smaller drops. Precipitation does not always arrive as liquid. When temperatures remain below freezing from cloud to ground, snow forms as water vapor freezes directly into ice crystals. The shapes of snowflakes depend on temperature and humidity and can appear as needles, plates, or the familiar star-like forms that emerge only under certain conditions. While it is said that no two snowflakes are alike, this is more a matter of probability than poetry. With countless snowflakes falling, some are bound to look nearly identical. If snow melts slightly while falling and then refreezes before reaching the ground, it becomes sleet. Freezing rain occurs when liquid drops freeze only after touching cold surfaces, often creating dangerous icy coatings in minutes. Hail is different from all of these. It forms inside powerful thunderstorms, where strong updrafts lift small ice pellets repeatedly through layers of supercooled water. Each pass adds another frozen layer, until the hailstone grows too heavy to remain suspended. Hailstones can range from very small to remarkably large, and are best admired from shelter. Water does not always need to fall from the sky to make itself known. Dew forms when the ground cools overnight, allowing moisture to condense on surfaces like grass. If temperatures drop further, this moisture becomes frost, tracing delicate ice patterns across leaves and windows. All of these movements, evaporation, condensation, and precipitation, belong to the water cycle. This endless circulation carries water from oceans into the air, back to the ground, and into rivers again. It has continued for billions of years and supports every form of life on Earth. Air does not need to be perfectly still for any of this to happen. Weather fronts are boundaries between different air masses, and they are often responsible for sudden and dramatic changes in the sky. When a warm, moist air mass encounters a cold, dry, When the lighter, warm air is forced upward, this lifting cools the air and triggers condensation and cloud formation, which often leads to rain. That is why so many weather changes begin with the passage of a front. The next time you look up and see a cloud drifting overhead, it helps to remember that it is not just a floating shape of white. It is the visible edge of an invisible process, a quiet balance of temperature, moisture, and motion unfolding all around you. Every droplet suspended in the air, every wisp of mist, every sudden burst of rain belongs to a vast and graceful water dance taking place above our head. And all of it begins with moisture in the air, unseen, often unnoticed, and endlessly vital. When the atmosphere decides to put on a show, thunderstorms are its most dramatic expression. They rumble, flash, pour, and sometimes hurl hail against rooftops with startling force. Yet for all their intensity, thunderstorms arise from simple ingredients: warm air, water, and electricity. At the center of every thunderstorm is warm, moist air, rising into cooler air above. This rising motion is called an updraft, and it usually begins with surface heating. Imagine a hot summer afternoon where sunlight has warmed the ground for hours. A pocket of air near the surface becomes warmer than the air around it and begins to rise because warm air is lighter. As it ascends, it expands and cools due to lower pressure. If the air holds enough moisture, it eventually reaches its dew point, the temperature where water vapor condenses into liquid droplets. This condensation releases latent heat, which gives the rising air an extra push upward. The effect is like adding fuel to an already lifting current. A cloud begins to form first as a gentle cumulus shape, and with enough moisture and instability, it can grow into a towering cumulonimbus cloud, stretching many miles into the sky. Inside this cloud, warm air continues to rise while cooler air and precipitation fall downward in what is known as a downdraft. This constant movement upward and downward powers the storm. Thunderstorms move through three stages, beginning with the cumulus stage, where air rises quietly and steadily. This is followed by the mature stage, when rain, lightning, and thunder appear, and updrafts and downdrafts coexist. Finally, the dissipating stage arrives when falling rain cools the surface and cuts off the supply of warm, rising air, causing the storm to fade. At the heart of this spectacle lies lightning, which is nature's method of balancing electrical charges. Inside the storm, tiny ice crystals and water droplets collide and become electrically charged. Lighter particles with positive charge are carried upward, while heavier, negatively charged particles sink. This separation builds an enormous difference in electrical potential until the air can no longer resist. The result is a sudden discharge of energy that lights the sky as lightning. Eventually, the storm weakens. When a hurricane moves over cooler water or land, it loses its heat source. Without warm water, the storm engine slows. Winds diminish, rain eases, and the system gradually dissipates. What remains is recovery and memory. While meteorologically, the storm has completed its life cycle, from warm ocean to rotating giant to fading rain, soaked remnant. Despite their differences, tornadoes and hurricanes are governed by the same fundamental principles. They arise from imbalance, from heat-seeking movement and pressure striving for equilibrium. They are dramatic reminders that weather, in all its forms, is driven by the atmosphere, endless attempt to find balance. In that sense, these events are not strange accidents, but natural outcomes of the same forces that keep Earth's atmosphere alive and endlessly moving. The next time thunder rolls across the sky, or satellite images show vast spirals of cloud, remember that these are the planet's strongest stories written in air and water. They are turbulent and sometimes frightening, yet also profoundly beautiful. They are reminders that the sky above us is not static but alive. Wind is the unseen sculptor of the world. You cannot see it directly yet. You feel it in your hair, hear it in the trees, and sometimes notice it when an umbrella suddenly turns inside out. Wind can be gentle or violent, playful or destructive. Yet at its heart, it is simply air in motion. Air that refuses to remain still. At its most basic level, wind exists because of differences in air pressure. When one region has higher atmospheric pressure, then another air naturally moves from the high pressure area toward the low pressure area. This movement is the atmosphere attempt to restore balance. The larger the pressure difference, the stronger the wind becomes. It is nature's version of tidying up, even if the result sometimes looks anything but tidy. Pressure differences can be imagined like hills and valleys. Air flows downhill from high pressure to low pressure, much like water would. But unlike water, air does not move in straight lines. Because the Earth is rotating, moving air is gently deflected by the Coriolis effect. In the northern hemisphere, air curves to the right. In the southern hemisphere, it curves to the left. This subtle deflection gives wind its graceful arcs and helps shape the global patterns visible from space. At the planetary scale, the story begins near the equator, where sunlight strikes the surface most directly. The intense heating causes warm air to rise, creating a persistent zone of low pressure. High above the surface, this rising air spreads poleward and eventually cools and sinks around 30 degrees north and south latitude. These sinking regions form belts of high pressure. From there, air flows back toward the equator along the surface, creating steady east to west winds known as the trade winds. These winds were so reliable that early sailors used them to cross entire oceans, sometimes deliberately, and sometimes by accident. In many ways, the age of exploration was carried forward on wind as much as on curiosity. Between 30 and 60 degrees latitude, the dominant winds reverse direction. Here the air flows from west to east, forming the westerly. These winds steer most of the weather systems that pass across North America and Europe. Closer to the poles, the circulation completes itself with the polar easterlies. These cold winds flow east to west, carrying frigid air from the Arctic and Antarctic toward lower latitudes. Together, these wind belts form part of the global circulation system, dividing the planet into vast moving streams of air. Wind is not only a global phenomenon, it is also intensely local. Some of the most fascinating winds arise from small-scale interactions between land, water, and terrain. Along coastlines, sea breezes provide a gentle daily rhythm. During the day, land heats faster than water. Warm air rises over the land, creating low pressure, and cooler air from over the ocean moves inland to replace it. At night, the pattern reverses as land cools more quickly. Then the sea and air flows back offshore. This simple exchange produces one of the most familiar and calming wind patterns on Earth. In mountainous regions, one knows the shape of the land itself. During the day, air along sunlit slopes warms and rises, drawing cooler air up from the valley in what is known as an anabatic wind. At night, the air cools, becomes denser, and flows downhill as a katabatic wind. This daily breathing of the mountains can produce dramatic temperature changes. For those who live among peaks and valleys, these winds are not curiosities, but a quiet part of everyday life. Some katabatic winds have earned names and reputations of their own. In southern France, the Mistral flows cold and dry down the Rhone Valley toward the Mediterranean. It can arrive with great force, sometimes exceeding 50 miles per hour, shaping the local climate and even the way towns are built. Homes are often designed with small protected windows turned away from its path, as if the architecture itself has learned to lean aside. In California, the Santa Ana winds sweep from the desert toward the coast during certain seasons. These winds are hot and dry, and they can turn a quiet landscape into a field of risk by drying vegetation and feeding wildfires. Their arrival brings both awe and unease, a reminder that wind, for all its grace, can also be dangerous. Among the most remarkable winds on Earth is the Chinook, often called the Snow Eater. Chinooks form along the eastern slopes of the Rocky Mountains when warm, dry air spills downward into the plains. In a matter of minutes, temperatures can surge dramatically, sometimes rising 40 degrees Fahrenheit in less than an hour. A winter morning can soften into a spring afternoon before the day is half done. It is as though the land itself has been warmed by a sudden breath. Wind can also be subtle and deceptive. Some gusts arrive without warning in the form of microbursts. These are powerful downdrafts that descend rapidly from thunderstorms and spread outward when they hit the ground. Their damage can resemble that of a tornado, knocking down trees, damaging buildings, and posing serious danger to aircraft. Then there are dust devils, small spinning columns of air that appear on hot, dry days. When the ground heats unevenly, they look like miniature whirlwinds twisting upward with dust and debris. They are not tornadoes and are usually harmless, lasting only moments as they wander across open ground. In deserts, they are common, playful in appearance and faintly mischievous. At the larger end of the scale are gales and cyclones, vast wind systems tied to strong areas of low pressure. A gale is typically defined by sustained winds above 39 miles per hour, strong enough to bend trees and make walking difficult. Cyclones, depending on their strength and location, can bring hurricane-force winds, heavy rain, and powerful storm surges. These are winds that reshape coastlines and leave lasting marks on the land. Not all winds announce themselves with noise or force. Some work quietly in the background, like the jet streams high above the Earth. These fast-moving ribbons of air circle the planet near the tropopause, flowing west to east at speeds of 100 to 200 miles per hour. They steer weather systems, guide storms, and even shorten or lengthen airplane journeys. Yet streams form along sharp temperature boundaries, such as the edge between cold polar air and warmer mid-latitude air. They shift north and south with the seasons, and their position can determine where storms travel and where droughts linger. When a jet stream bends or stalls, it can trap weather patterns in place, leading to long heat waves, extended rain, or stubborn cold. Though invisible wind shapes the world in countless ways, it carries moisture across continents, spreads seeds and pollen, and slowly wears stone into sand. It sculpts dunes in deserts and drifts of snow in polar regions. It pushes sailboats over oceans and spins turbines across plains. It can be a soft whisper or a force of transformation. Throughout history, humans have watched the wind, learned from it, and depended on it. Ancient sailors trusted it to carry them across unknown seas. Farmers read its shifts as signs of change. Today, we harness it as a source of clean energy, turning its endless motion into electricity without flame or smoke. The wind moves on endlessly unseen, yet ever present, shaping the world one breath at a time. Wind also plays a quiet but meaningful role in regulating temperature across the planet. It carries warmth away from hotter places and brings cooler air into regions that would otherwise overheat. On a hot day, a breeze can feel like relief arriving just in time. On a cold day, that same breeze can cut straight through fabric and skin. This sensation is described by the idea of wind chill, which reflects how cold it feels when moving air pulls heat away from your body. Wind chill does not actually lower the air temperature, but it changes how quickly your body loses warmth. Though wind can appear unpredictable, it follows clear physical rules. It moves along paths shaped by pressure differences guided by temperature contrasts terrain and the steady rotation of the earth. From the faint rustle of leaves to the long howl of a winter storm wind is a language the planet speaks without pause. It is constant and expressive, shaping the air around us, even when we barely notice. The next time trees sway outside your window, or a breeze brushes your cheek, it is worth pausing to acknowledge that unseen presence. Wind is always moving, always reshaping, and always reminding us that the atmosphere is alive. When winter arrives, it does not creep in unnoticed. It transforms the world in quiet and dramatic ways. Trees stunt bare ponds seal themselves with ice, and the air sharpens with cold. Snow settles on rooftops, muffles sound, and turns familiar landscapes into soft pale scene. Beneath this calm surface lies complex science. Snow, ice, sleet, and freezing rain are not simply different kinds of winter weather, but signatures of the atmosphere's coldest states. Snow begins its journey high above the ground. Each snowflake starts as a tiny dust particle suspended in the air. Water vapor condenses directly onto this speck and freezes, forming an ice crystal. As the crystal drifts through the cloud, more vapor freezes into it, allowing the flake to grow. Its final shape depends on temperature and humidity, which shift constantly during its descent. This is why no two snowflakes are truly identical, and why variety emerges from simple rules. Most snowflakes form six-sided patterns. This hexagonal symmetry comes from the molecular structure of water. Each H2O molecule bonds at precise angles, creating repeating geometric forms. Some flakes grow into flat plates, others stretch into needles or branch into stars. Under magnification, they reveal remarkable detail shaped only by air moisture and temperature. Snow feels light, but its weight accumulates quickly. A single cubic foot of fresh snow can weigh between 5 and 15 pounds, depending on how much water it contains. When countless flakes settle together, even a gentle snowfall can place heavy strain on roofs and branches. Wet snow holds more moisture and is denser than dry powder, making it especially heavy. Not all frozen precipitation falls so gently. Sleet forms when snowflakes melt partially as they pass through a warm layer of air and then refreeze before reaching the ground. The result is small ice pellets that bounce when they land. These pellets create a crunchy, slippery surface that is inconvenient but usually manageable. Freezing rain follows a similar path, but with a more dangerous outcome. Snow melts completely into rain as it passes through warm air aloft. Near the ground, it encounters a shallow layer of cold air. The droplets do not have time to refreeze while falling. Instead, they remain liquid and supercooled until they strike a surface. Upon contact, they freeze instantly, coating roads, trees, and power lines in smooth, clear ice. The instant supercooled rain touches a surface, whether it is a sidewalk, the smooth curve of a car hood, or the fragile reach of a tree branch, it freezes, immediately spreading outward into a clear, glassy skin of ice. This thin glaze can be hauntingly beautiful, transforming streets and landscapes into shimmering sculptures, yet it carries serious consequences beneath its shine. Roads become dangerously slick, sidewalks turn into skating rinks, and tree branches bend and sag under the growing weight. Unlike snow, which can be pushed aside, compacted, or cleared, ice clings tightly to everything. It meets refusing to let go. This stubborn grip is why freezing rain is among the leading causes of winter power outages, snapping limbs and pulling power lines down as the ice thickens hour by hour. Another quieter presence of winter is frost, the delicate white lace that appears during calm, clear mornings. Frost forms when surface temperatures fall below the dew point and also below freezing, allowing water vapor in the air to bypass the liquid state entirely and settle directly as solid ice crystals. The result is a fragile coating of white spreading across grass windows and rooftops in intricate silent patterns. A more dramatic variation is hoarfrost, which develops when moist air remains still and temperatures stay well below freezing. Under these rare conditions, ice crystals grow outward into elaborate shapes resembling feathers, needles, or ferns, turning entire landscapes into something that feels more imagined than real. Unlike snow, frost does not fall from the sky. It grows patiently in place, shaped only by temperature and humidity. In the coldest regions, winter sometimes introduces ice fog, a phenomenon both eerie and quietly enchanting. Ice fog forms when tiny droplets of supercooled water suspended near the ground freeze into microscopic ice crystals. This frozen mist lingers low, diffusing light and limiting visibility, much like ordinary fog, but with a faint, crystalline shimmer. Ice fog is most common in places such as Alaska and northern Canada, where temperatures regularly sink far below zero. It can transform streetlights into glowing halos and give the air itself a silvery glow, while quietly making travel far more difficult. Wind adds another dimension to winter's bite. Cold air alone is uncomfortable, but cold air in motion can become punishing. This effect is described by wind chill, which reflects how cold it feels. When wind speeds up the loss of heat from your skin, your body naturally warms a thin layer of air close to the skin, creating a small pocket of insulation. Wind strips this layer away, forcing your body to work harder to maintain its temperature. The stronger the wind, the faster heat is lost. For example, an air temperature of 20 degrees Fahrenheit combined with a 15-mile-per-hour wind can feel closer to 5 degrees. Wind chill does not change the actual temperature, but it dramatically increases the risk of frostbite and hypothermia, turning wind from a background presence into an active threat. Among the most formidable expressions of winter weather are blizzards. A blizzard is not defined solely by snowfall, but by a combination of wind, reduced visibility, and duration. Meteorological standards require sustained winds, or frequent gusts of at least 35 miles per hour, visibility reduced to a quarter mile or less in conditions lasting 3 hours or more. In some cases, blizzards occur without any new snow, driven instead by powerful winds lifting loose snow into the air. These storms can immobilize cities, strand travelers, and create whiteout conditions where direction and distance vanish, making even short journeys dangerous. Yet despite their intensity, blizzards arise from the same fundamental ingredients as other storms: cold air, moisture, and atmospheric instability. Snow squalls present a different challenge altogether. These brief but intense bursts of snow and wind form rapidly, often with little warning. Visibility can collapse in seconds, temperatures can drop sharply, and roads can become slick almost instantly. Snow squalls may last only a short time, but their sudden arrival makes them especially hazardous. Anyone who has driven from clear skies into blinding snow within a single mile has likely encountered one. Despite its hardships, winter weather plays a vital role in Earth's systems. Snowpack stored in mountain ranges acts as a natural reservoir, releasing fresh water. Slowly as it melts in spring, ice and snow reflect sunlight back into space, helping regulate global temperatures and balance the planet's energy budget. Winter may seem harsh and unforgiving, yet it is essential, shaping landscapes, sustaining ecosystems, and reminding us that even the coldest seasons are part of the planet's quiet, ongoing rhythm. Even frost and snow play a quiet, protective role by insulating the soil and shielding plant roots from the harshest cold. So the next time you see your breath drift into the air, or catch a snowflake resting briefly on your glove, remember that you are witnessing one of the atmosphere's most intricate and delicate performances. Every icy detail, from a frost-tipped leaf to a snow-covered field, is shaped by precise and elegant physics unfolding patiently in silence. Behind the hush of falling snow lives a story of temperature, motion, moisture, and time, written in crystals and carried gently by the wind. Some weather arrives without drama and without warning signs of thunder, lightning, or heavy snow. It comes as a soft thickening of the air, a pale gray veil that blurs distance and quiets sound. This is fog, the most subtle and mysterious expression of the atmosphere. Fog does not roar or strike, but drifts and curls, reshaping the familiar into something strange and intimate. At its heart, fog is simply a cloud that has settled at ground level, forming when water vapor condenses into countless microscopic droplets suspended in the air near the surface. These droplets are too small to fall as rain, so they linger, floating and scattering light in every direction, shrinking visibility and drawing the world inward into a quieter, softer place. There are many kinds of fog, each shaped by a different balance of temperature, humidity, terrain, and time. Radiation fog forms on calm, clear night, when the ground cools quickly, chilling the moist air resting just above it until condensation begins and fog quietly gathers, often in valleys where cool air settles. As morning sunlight returns, the ground warms, the air lifts, and the fog slowly dissolves like a curtain rising from a stage. Advection fog forms when warm, moist air moves across a colder surface, cooling from below until it reaches saturation and spreads in wide blankets, often along coastlines. Upslope fog appears when moist air is pushed upward along hills or mountains, cooling as it rises until fog forms and clings to the slopes, sometimes lingering for long hours. Evaporation fog, sometimes called steam fog, forms when cold air passes over warmer water, causing moisture to condense instantly into curling, ghost-like wisps. Freezing fog occurs when temperatures are below freezing, but fog droplets remain liquid until they touch a surface and freeze on contact, creating rough white coatings of ice that transform landscapes into silent, frozen sculptures shaped by wind and cold. Each form of fog tells the same quiet story of cooling air condensing moisture, and the atmosphere seeking balance without urgency or sound. Humidity plays a quiet but powerful role in how heat is felt by the body. When the air is heavy with moisture, the body struggles to cool itself through sweating. Sweat is the body's natural cooling system, evaporating from the skin and carrying heat away. When the air is already saturated, this evaporation slows, and the heat lingers, making the day feel far warmer than the thermometer suggests. This is why scientists use the heat index, a measure of how hot it feels. When humidity is taken into account, much like wind chill in winter, on a day when the actual temperature reaches 95 degrees Fahrenheit and the relative humidity sits near 55%, the heat index can climb closer to 110 degrees. This is the kind of heat that softens pavement, slows thought, and makes every movement feel heavier than it should. Prolonged exposure to such heat is not only uncomfortable, but dangerous, especially for older adults, children, and those with existing health conditions. Heat exhaustion and heat stroke can develop when the body can no longer regulate its internal temperature. Symptoms may include dizziness, nausea, rapid heartbeat, and confusion. During extended heat waves, emergency services often see a sharp rise in hospital visits. This is why shaded spaces, cooling centers, flowing water, and even a simple fan can quietly become tools of survival. Now, consider drought, the slow, silent companion to extreme heat. Where heat waves arrive loudly, droughts creep in unnoticed. A drought is a prolonged period of below-average rainfall leading to water shortages across land and communities. It does not announce itself with storms or alarms, but begins simply when rain fails to arrive. Droughts may last weeks, months, or even years, building gradually, or appearing after a dry winter or a failed rainy season. Their impacts depend on location, but their reach is wide. Rivers shrink, soil cracks, reservoirs recede, and crops strain under the stress. In severer cases, drought can lead to famine, forest loss, and human migration. When land can no longer sustain life, scientists describe drought in several forms. Meteorological drought reflects a lack of precipitation. Agricultural drought affects soil moisture and crop growth. Hydrological drought appears when rivers, lakes, and underground aquifers fall to low levels. Socioeconomic drought emerges when water shortages begin to disrupt economies and daily life, raising food prices, limiting irrigation, and changing how cities function. Many forces can contribute to drought. Large-scale atmospheric patterns such as El Nino and La Nina can shift rainfall around the globe. El Nino often brings dry conditions to regions like Australia and Southeast Asia. La Nina can alter jet stream paths and reduce rainfall in areas such as the southwestern United States. Persistent high-pressure systems, ocean temperature changes, and long-term climate shifts also play a role. Rising global temperatures intensify these effects by increasing evaporation rates. Water leaves soil, lakes, and vegetation more quickly even when rain does fall. Sometimes heavy rain follows a drought, but the hardened ground cannot absorb it, leading to runoff and flash flooding instead of relief. Heat waves and drought often reinforce one another. Dry land reduces evaporation, allowing temperatures to rise further. With little moisture to absorb solar energy, more heat goes directly into warming the ground and air. This feedback loop can trap regions in long cycles of hot, dry weather. Heat waves and droughts are natural parts of Earth's climate system and have existed for millions of years. Yet in recent decades, their frequency and intensity have increased in many regions. Scientists link this trend in part to climate change, as a warmer atmosphere holds more energy and makes extremes more likely. In response, adaptation becomes essential. Cities invest in trees, green roofs, and reflective surfaces to reduce heat. Farmers turn to drought-resistant crops and more efficient irrigation. Water conservation becomes part of everyday life, where rain can no longer be assumed. Even so, there is beauty within the dry and the hot. Cracked earth reveals intricate patterns shaped by time. Grasses bent in wind beneath wide skies, and trees stand silhouetted against shimmering horizons. Heat can paint sunsets in deep, burning colors as the sun lowers through hazy air. And when rain finally returns after long absence, it feels less like weather and more like reunion. So when the air grows still and the heat settles in, take a slow breath and listen to the quiet story the atmosphere is telling. You're witnessing the quieter side of weather, where change happens without thunder or spectacle, and where heat and dryness reshape the world in silence. These forces rarely announce themselves with flashing skies or roaring winds yet. Their influence runs deep etched into soil memory and the long patient story of the atmosphere, forever seeking balance. While some weather dazzles with sound and fury, others choose to enchant gently, appearing in still moments after storms, or when sunlight meets moisture at precisely the right angle. These are the subtle wonders of the sky, the optical illusions and soft spectacles that reveal the atmosphere, not only as a system of physics, but as a quiet artist at work. The most familiar of these wonders is the rainbow, which is not an object you can touch or chase, but an interaction between light, water, and perspective. When sunlight enters a raindrop, it bends, reflects off the back of the droplet, and bends again as it leaves. Through this process, the light separates into its component colors: red, orange, yellow, green, blue, indigo, and violet, each bending by a slightly different amount. Red bends the least, violet the most, and together they form a circle of color that usually appears as an arc because the ground hides the rest. From high places like mountains or airplanes, the full circle can sometimes be seen suspended in the air. A primary rainbow always appears about 42 degrees opposite the sun, meaning the sun must be behind you and moisture must be ahead. This also means a rainbow cannot be reached because it moves with you. Each person sees a different rainbow shaped by the light entering their own eyes, making it a deeply personal event, made entirely of light. Sometimes a second fainter rainbow appears outside the first formed, when light reflects twice inside the raindrop before emerging in the secondary arc. The colors are reversed, and between the two lies a darker region known as Alexander's Band, first described by an ancient Greek observer. When sunlight meets ice instead of rain, a different family of sky art appears. High above the earth, thin clouds made of ice crystals bend and reflect light into halos, sundogs, and pillars. A halo forms as a pale luminous ring around the sun or moon when light passes through hexagonal ice crystals, bending at a specific angle. Sundogs appear as bright, colorful companions to the sun, often glowing on either side. When the crystals are aligned just right, light pillars rise vertically from light sources. When flat ice crystals drift slowly through calm air, reflecting light upward into shimmering columns. Another delicate phenomenon is the glory, which appears as small concentric rings of color surrounding the shadow of an observer cast onto cloud or fog. Glories are often seen from airplanes, where the shadow of the aircraft is encircled by softly glowing rings that seem to breathe with motion. These quiet displays do not roar or rush, yet they remind us that even in stillness the atmosphere is alive, painting fleeting masterpieces from light, water, and ice. The effect is created when sunlight is backscattered and interacts with countless tiny droplets suspended within cloud or fog. Pilots and passengers often call this sight the glory of the pilot, because it commonly appears encircling the shadow of an aircraft cast onto clouds below. Closely related to glories are coronas, which form when light diffracts around individual water droplets, creating tight, luminous rings around the sun or moon. Unlike halos, coronas are small and compact, hugging closely to the bright source and often appearing pearlescent when seen through thin cloud or mist. Then there is the sky's more dramatic yet still gentle display known as crepuscular rays, sometimes called God rays. These beams of sunlight appear to fan outward from the sun, most often at sunrise or sunset when the sun sits low and clouds or terrain partially block its light. The rays only seem to spread outward because of perspective, much like parallel railroad tracks appearing to converge in the distance. Crepuscular rays form when sunlight streams through gaps in clouds or mountains and illuminates particles in the air such as dust, moisture, or pollen, creating alternating bands of light and shadow. The contrast between brightness and darkness gives the impression of radiant shafts of light, as though the sky itself were breathing illumination outward. As twilight deepens, another rare optical moment may appear, known as the green flash. This fleeting event occurs just after sunset or just before sunrise, when only the very top edge of the sun is visible. For a second or two, that final sliver can glow green as the atmosphere bends light like a prism. Blue and green wavelengths bend more strongly than red and orange, and under the right conditions, green light briefly separates and becomes visible. The moment is short and easily missed, yet it has been treasured by sailors and sky watchers for generations. There are also lunar rainbows, often called moonbows, which form when moonlight rather than sunlight passes through rain or mist. Because moonlight is far weaker, these bows are pale and subtle, often appearing white or silvery to the naked eye. Under the right conditions, with a bright full moon moisture in the air, and the moon low behind the observer, faint colors can sometimes be seen, especially in long exposure photographs. All of these phenomena are gentle reminders that light and atmosphere are always in conversation. Even when unnoticed, the sky is constantly shaping color, bending reflection and shadow. When conditions align, the atmosphere becomes a canvas where physics paints quietly, arcs, rings, pillars, and flashes. No special tools are required to witness these moments. Only curiosity, patience, and the habit of looking up. A rainbow after rain, a halo around a winter sun, a soft glory floating around a shadow. Each one is a quiet message from the sky. Nature does not speak only in thunder and lightning, but also in shimmer, hue, and glow. Weather shapes the world, but light paints it. And from time to time, the atmosphere becomes not just a system, but a gallery. Weather can feel deeply personal and intensely local when sunshine bathes one place, while rain falls just a few miles away. Yet at the same time, weather is profoundly global, shaped by latitude, oceans, mountains, and the slow turning of the planet itself. Across the world, the same sky behaves in strikingly different ways, creating climates as varied as the landscapes beneath them. From heavy monsoon rains to vast dust-filled winds, each region carries its own climatic signature. One of the most dramatic and essential global systems is the monsoon. The word monsoon comes from the Arabic term musim, meaning season, and it describes a seasonal reversal of wind rather than rain itself. Monsoons arise from temperature differences between land and sea that shift with the seasons. When land heats faster, then ocean air rises over continents, drawing in moist winds from the sea. These winds carry immense amounts of water vapor, which condense and fall as sustained rains, though often associated with flooding and storms. Monsoons are fundamentally a rhythm of balance, delivering water that sustains agriculture ecosystems and millions of lives year after year. Nowhere is the monsoon more powerful than in South Asia, particularly across India, Bangladesh, Nepal, and the surrounding countries. During the summer months, the land heats up far more quickly. then the surrounding oceans, creating a vast area of low pressure over the Indian subcontinent. Moist air from the Indian Ocean rushes inland to fill this imbalance, and as it collides with the towering Himalayas, it is forced upward. As the air rises, it cools and condenses into immense columns of rain. The result is not a brief storm, but weeks or even months of nearly continuous precipitation. The monsoon is essential to life in the region. It waters crops, fills rivers, and recharges underground aquifers that support hundreds of millions of people. At the same time, it carries serious risks. Floods overflow riverbanks, landslides sweep down hillsides, and daily life can be disrupted for long periods. Even so, after the scorching and relentless heat of the pre-monsoon summer, the arrival of the rains is welcomed by many as a necessary and life-giving force. Farther east countries such as Thailand, Vietnam, and the Philippines also experience monsoon patterns, though their timing and intensity vary from place to place. In East Asia, the East Asian monsoon brings hot, humid summers and cold, dry winters, shaping agriculture, infrastructure, and urban planning across the region. In the southern hemisphere, northern Australia experiences its own monsoon system. During the austral summer, typically from December through March, tropical storms and torrential rain sweep across the region. Locals call this season simply the wetter time, marked by dramatic cloud towers, intense rainfall, and frequent lightning that illuminates the night sky. Moving away from rain-soaked regions, desert climates present a very different expression of weather, one defined by extremes rather than abundance. Deserts are often imagined as empty and lifeless, yet they are atmospherically dynamic environments. In the Sahara, the world's largest hot desert, daytime temperatures can exceed 120 degrees Fahrenheit, while nighttime temperatures may drop by 40 or even 50 degrees. This dramatic swing occurs because dry air holds little moisture, and without vegetation or water to store heat, the ground rapidly releases warmth once the sun sets. Deserts are also known for their dust storms called haboobs in parts of North Africa and the Middle East. These towering walls of dust form when cold downdrafts from thunderstorms strike the ground and push loose sand and soil into the air. Such storms can stretch for miles, reduce visibility to near zero, and sweep through cities with startling speed, blotting out the sun and coating everything in fine grit. Similar events occur in Australia, where winds can carry red dust across vast distances, and in the American Southwest, where late summer thunderstorms frequently trigger dramatic dust storms. At high latitudes, the atmosphere tells yet another story. In the Arctic and Antarctic, weather is dominated by ice, wind, and extreme cycles of light and darkness. Winters bring months of near total darkness and bitter cold, while summers are marked by continuous daylight and surface melting. One of the defining features of polar weather is the katabatic wind, a flow of dense, frigid air that descends downhill from ice-covered plateaus under the force of gravity. In Antarctica, these winds can reach hurricane strength, sweeping snow across the frozen landscape and creating blinding whiteout conditions. Despite their icy appearance, the polar regions are technically deserts because they receive very little precipitation. Much of the snow and ice there fell thousands of years ago and has never melted. When snowfall does occur, it often appears as tiny ice crystals drifting gently to the surface, almost too delicate to notice against the vast white expanse. Closer to the equator, the atmosphere becomes energetic and predictable in a different way. Tropical regions such as the Amazon basin, the Congo basin, and much of Southeast Asia are home to dense rainforests sustained by frequent and heavy rainfall throughout the year. Here, convectional rainfall dominates. Intense solar heating causes warm, moisture-laden air near the surface to rise, rapidly condensing into towering clouds by afternoon and producing near-daily thunderstorms. These storms are typically short-lived, but intense, releasing bursts of rain that nourish some of the most biodiverse ecosystems on Earth. The consistency of tropical weather allows dense vegetation to thrive, creating layered forest canopies and supporting a continuous cycle of growth, decay, and renewal. Travel only a little farther from the equator, and the atmosphere begins to change its rhythm. Here lie the savanna regions where rainfall arrives not steadily, but seasonally, shaping landscapes ruled by grasses and roaming herds. Long dry months stretch the land thin, and then sudden wet seasons arrive, bringing renewal and growth. In these places, timing is everything. When the rains come too early or too late, entire ecosystems feel the shift as food chains tremble, and survival hangs on delicate balance. Across the ocean's island nations develop weather patterns entirely their own, guided by trade winds, tropical storms, and moving seas. In the vast Pacific, one of the most influential climate patterns on Earth quietly pulses beneath the surface. This is the El Niño Southern Oscillation, known simply as ENSO. During El Niño, warm ocean waters drift eastward, disrupting rainfall across South America, Australia, Southeast Asia, and even parts of Africa. In contrast, La Niña brings cooler waters and shifts weather patterns in the opposite direction, often intensifying rain in some regions and deepening drought in others. Ocean currents themselves act like planetary conveyor belts, carrying heat across the globe. The Gulf Stream in the Atlantic and the Kuroshio Current in the Pacific transport warm tropical water toward higher latitudes, softening climates and shaping weather far from their origins. This is why places like the United Kingdom remain relatively mild despite their northern position, while other regions at the same latitude endure far harsher conditions. In mountainous landscapes, elevation becomes the dominant storyteller. As air is forced upward over mountain ranges such as the Andes, the Himalayas, or the Rockies, it cools and releases its moisture. Rain and snow fall generously on the windward slopes, while the descending air on the opposite side warms and dries, creating what is known as a rain shadow. These shadows give rise to some of the driest places on Earth, including the Atacama Desert in Chile, tucked just beyond the towering Andes. Mountains do not simply shape scenery. They sculpt climate, dictate vegetation, and decide where rivers will run or never appear at all. Along coastlines, the presence of the ocean tempers extremes. Water heats and cools slowly, lending coastal regions milder winters and cooler summers. Inland areas lacking this maritime influence experience sharper contrasts, with scorching summers and biting winters. Central Asia is a striking example, swinging between intense seasonal extremes, while coastal Norway remains comparatively gentle thanks to the steady warmth delivered by ocean currents. Zoom closer still, and the atmosphere reveals its finest details through microclimates. A shaded ravine may remain cool and damp while a nearby hillside bakes in sunlight. A city street lined with glass and concrete can trap heat and feel warmer than a neighboring park only steps away. Vineyards planted on different slopes of the same hill can yield grapes with distinct character, shaped by subtle differences in sun, wind, and moisture. These small variations remind us that weather is not only global, but deeply local, woven into every contour of the land. Every region on Earth carries its own atmospheric signature, shaped by latitude, terrain, ocean proximity, and circulation patterns. Yet beneath this immense diversity, the same simple rules apply everywhere. Heat rises. Air flows from high pressure to low. From the driest desert to the wettest rainforest, the physics remain constant. Even as the outcomes vary endlessly. So wherever you find yourself, whether watching lightning stitch the sky, above a tropical forest waiting out a dust storm, in a sun-scorched desert, or standing beneath the quiet stars of a polar night, you are living one chapter of a single global story, a story written in wind and water and sunlight and shadow woven gently and endlessly around the planet. And after all this wandering through clouds, storms, heat, and silence, a final question remains. How do we know what comes next? How can we glimpse tomorrow's sky before it arrives? Weather forecasting may appear to be part intuition, part guesswork, but in truth it is a careful listening to the atmosphere itself, a patient practice built on physics observation and patterns slowly revealed. It is how we learn to read the sky, not as chaos, but as conversation. Weather forecasting is one of the most demanding things humans attempt on a daily basis, and also one of the most quietly useful. To say anything meaningful about tomorrow, meteorologists must first understand today with remarkable precision. That means not only knowing what the sky looks like above one city, but holding a clear and detailed picture of conditions across the entire planet. The atmosphere is a connected system, and weather does not respect borders. A cluster of storms over Texas may be tied to a pressure system that later shapes conditions in New York, while a disturbance over the Pacific can influence Europe days later. Forecasting always begins with careful observation, creating a living snapshot of the present before gently projecting it forward. To build this snapshot, scientists rely on a vast global network of instruments. At the surface, thousands of weather stations are scattered across continents, islands, ships, and remote regions. These stations continuously measure temperature, humidity, air pressure, wind speed, wind direction, and precipitation. Some operate automatically, while others are maintained by trained observers, but all transmit their data into centralized systems every few minutes. Together they form a constantly shifting map of the lower atmosphere, revealing how conditions vary from place to place and how quickly they are changing. Above the surface, meteorologists gather information using weather balloons, formerly known as radio sondes. These balloons are launched from hundreds of locations around the world, usually twice each day. As they rise through the atmosphere, they carry instruments that record temperature, moisture, and wind at different heights. Many reach altitudes of around 20 miles before bursting. This data is essential because weather behaves very differently at different levels of the atmosphere. Calm day near the ground can hide strong winds, or unstable air above in those hidden layers often determine whether storms will grow or fade away. Understanding this vertical structure is a key step in predicting what happens next. The greatest leap forward in forecasting came from space. Weather satellites orbiting Earth provide continuous global coverage that ground-based systems alone could never achieve. Some satellites remain fixed over the same region, allowing meteorologists to watch clouds evolve in real time. Others orbit from pole to pole gradually, scanning the entire planet. These satellites do far more than take images. They measure sea surface temperatures, track storm development, estimate atmospheric moisture, and monitor snow-cover wildfires and volcanic ash. The animated cloud maps and swirling systems seen in forecasts are built from this constant flow of satellite data. Closer to the ground, radar plays a vital role, especially for short-term forecasts. Weather radar sends out pulses of radio energy that bounce off raindrops, snowflakes, or hailstones and return to the radar station. By studying these signals, meteorologists can see where precipitation is falling, how intense it is, and how fast it is moving. Doppler radar adds another dimension by detecting motion within storms, which helps identify areas of rotation that may signal developing tornadoes. This technology allows warnings to be issued minutes before severe weather strikes, sometimes with just enough time to save lives. All of this information, billions of measurements collected every day, is fed into numerical weather prediction models. These models are vast computer simulations that attempt to recreate the behavior of the atmosphere using the laws of physics. The planet is divided into a three-dimensional grid, with each cell representing a small volume of air. For every cell, the model calculates how temperature, pressure, wind, and moisture will change based on neighboring cells and the flow of energy through the system. The calculations are extraordinarily complex and require powerful supercomputers to solve equations describing fluid motion, heat transfer, radiation, and cloud formation again and again. Several major models are used around the world, including the Global Forecast System in the United States, the European Center for Medium-Range Weather Forecasts, and the UK Met Office model. Each has its own strengths and design choices, and forecasters often compare them rather than trusting a single result. Even with this technology, forecasts are never perfect. The atmosphere is a chaotic system, meaning tiny uncertainties in initial observations can grow over time and lead to very different outcomes. This sensitivity is often described as the butterfly effect, the idea that a very small change can eventually influence weather far away. Because of this, forecasting is not about certainty but probability and informed estimate shaped by observation, physics, and experience, and constantly refined as new data arrives. It is a poetic way of saying that even the smallest measurement uncertainties can grow into much larger differences as time passes. To cope with this natural uncertainty, meteorologists rely on ensemble forecasting, where a weather model is not run just once, but many times with slightly altered starting condition. This creates a range of possible futures that can be compared and analyzed to find the most likely outcome. When most of the model runs agree, the forecast carries high confidence, and when they spread apart, it signals a more uncertain and delicate situation. Despite the power of computers, weather forecasting is not left to machines alone. Human expertise remains essential as meteorologists interpret model results, compare multiple forecasts, and apply local knowledge that models cannot fully capture. A computer may not recognize how a specific mountain pass channels wind, or how a certain coastline reliably breeds fog, but an experienced forecaster often does. This blend of physics, computation, and human judgment is what turns raw data into meaningful guidance. Forecast accuracy has improved enormously over recent decades, with a modern 3-day forecast now matching the accuracy of a 1-day forecast from the 1980s. 5-day forecasts are generally reliable, and even 10-day outlooks can reveal useful trends, though fine details become increasingly uncertain. As forecasts extend further into the future, small uncertainties multiply, and the atmosphere's inherent chaos softens the picture. Short-term forecasting, sometimes called nowcasting, focuses on rapidly changing events like thunderstorms, tornadoes, or sudden downpour. These forecasts depend heavily on high-resolution radar, frequent model updates, and dense local observations. They allow meteorologists to issue watches and warnings in near real-time, helping communities respond to severe weather with precious minutes of preparation. Alongside this approach, probabilistic forecasting has become more common, offering likelihoods rather than certainties. Instead of promising rain, a forecast may suggest a 70% chance, acknowledging uncertainty while still providing useful information. This method reflects how forecasting truly works and helps people make better everyday decisions. Weather prediction reaches far beyond daily convenience and plays a critical role in aviation, shipping, agriculture, emergency planning, and energy management. Pilots use forecasts to avoid turbulence, and storms farmers depend on rainfall. Outlooks to plan irrigation and emergency services rely on early warnings to prepare for hurricanes, floods, and wildfires. New technologies, including machine learning and artificial intelligence, are now being woven into forecasting systems, analyzing vast datasets and identifying subtle patterns that improve accuracy. These tools do not replace traditional methods, but strengthen them, becoming valuable companions in the meteorologist's toolkit. You also play a part in this global effort. Through smartphones, apps, and connected devices, millions of people now share local observations that fill gaps between official stations. These reports create richer, more detailed snapshots of conditions on the ground, helping forecasts stay current and precise. So when you glance at a simple weather icon showing a temperature and a chance of rain, remember what stands behind it. Satellites circling the planet, balloons drifting miles above Earth, supercomputers solving billions of equations, meteorologists refining interpretations, and countless everyday observers noticing subtle shifts in wind or cloud. It is a vast, quiet collaboration, all aimed at reading the sky. While our ability to predict weather has never been stronger, the atmosphere itself is changing. Weather has always shifted from calm to stormy, from gentle to fierce, yet over the past century, a deeper transformation has become clear. This change unfolds not over hours or days, but across decades and generations, and it is known as climate change. To understand its influence, we must distinguish between weather and climate. Weather is the atmosphere's momentary mood, the rain today, the heat tomorrow, the breeze brushing past your skin. Climate is the atmosphere's long-term character, the average patterns shaped over 30 years or more. Climate tells us what is typical for a region, how seasons usually behave, and how often extremes occur. Earth's climate has never been static, and over millions of years, it has shifted between ice ages and warmer periods, driven by natural forces like orbital changes, volcanic activity, and variations in solar energy. What makes the current change different is its speed and its cause. Since the late 19th century, human activities have released large amounts of greenhouse gases into the atmosphere, trapping additional heat. As a result, the average global temperature has risen by more than 2 degrees Fahrenheit. Though that number may sound small, for a system as vast and sensitive as Earth's climate, it represents a profound shift, setting the stage for changes in weather patterns across the globe. This warming is largely driven by the greenhouse effect, a natural process in which certain gases trap heat within the atmosphere and keep the planet warm enough to support life. The key greenhouse gases are carbon dioxide, methane, nitrous oxide, and water vapor. Among these, carbon dioxide plays the central role in today's climate story. It is released when fossil fuels such as coal, oil, and natural gas are burned. Deforestation intensifies the problem by reducing the number of trees available to absorb carbon dioxide from the air. As concentrations of greenhouse gases rise, more heat becomes trapped in the atmosphere. The result is a warming planet. This warming does not simply mean hotter summers. It means widespread changes in weather patterns across the globe. One of the most immediate examples is the increase in heat waves. These periods of intense, prolonged heat are becoming more frequent, more severe, and longer lasting. In many regions, heat waves that once occurred only once every 20 years now appear every few years, or even every year. Urban heat islands amplify this trend, making cities especially vulnerable. At the same time, nights are warming faster than days. This detail may seem small, but its effects are significant. Warmer nights provide less relief from daytime heat, increasing stress on the human body and reducing the ability of crops and animals to cool down. Heat lingers rather than releasing its grip. Precipitation patterns are shifting as well. Some regions are receiving more rainfall, while others are becoming increasingly dry. Warmer air can hold more moisture, roughly 4% more, for every 1 degree Fahrenheit increase in temperature. This means that when rain does fall, it often falls harder. Extreme rainfall events with intense downpours are becoming more common. Overwhelming drainage systems, flooding streets, and washing away soil. More moisture in the air does not mean more rain everywhere. In many areas, especially those already prone to drought conditions, are becoming drier. Longer dry spells combined with higher temperatures lead to parched soils, shrinking rivers, and stressed ecosystems. Regions such as the southwestern United States, southern Europe, and parts of Africa are experiencing more frequent and severe droughts. This pattern of intensification in both directions is a defining feature of climate change. Wet areas tend to become wetter, while dry areas become drier. It is not simple warming, but a reshuffling of the entire atmospheric system. Storm behavior is changing too. Warmer ocean temperatures provide additional energy for tropical storms, increasing the potential for stronger hurricanes, cyclones, and typhoons. Evidence suggests that while the total number of storms each year has not risen dramatically, their intensity has. Category 4 and Category 5 storms capable of catastrophic damage are becoming more common. These storms also carry more moisture, which leads to heavier rainfall when they reach land. Hurricanes such as Harvey in 2017 and Florence in 2018 released extraordinary amounts of rain, causing severe flooding far inland from the coast. In higher latitudes, winter weather is also being reshaped. A warmer atmosphere does not eliminate snow, and in some cases can even increase snowfall because the air carries more moisture. However, the timing and character of winter are changing. Snow seasons are beginning, later ending earlier, and snowpack in mountain regions is shrinking. This loss matters because snowpack acts as a natural reservoir, releasing water slowly through spring and summer. Climate change is also influencing the jet stream, the high-altitude river of wind that steers weather systems around the planet. As the Arctic warms faster than lower latitudes, a process known as Arctic amplification, the temperature contrast between the poles and the equator weakens. This can slow the jet stream and cause it to meander more dramatically. A slower, more irregular jet stream can allow weather systems to stall. Rainstorms may linger over one area for days, or heat waves may remain locked in place. These stalled patterns have been linked to recent extreme events, including European heat waves and prolonged flooding in the United States. Sea level rise adds another layer of impact. While not weather itself, it strongly shapes how weather is experienced, especially along coastlines. As glaciers melt and oceans warm and expand, sea levels have risen by about 8 inches since the late 1800s. Higher sea levels allow storm surges and tidal flooding to reach farther inland, affecting more people and infrastructure. Climate change also shapes wildfires, not by striking the match itself, but by quietly preparing the landscape for ignition and spread. Hotter temperatures dry out soils, earlier snowmelt leaves, forests exposed for longer periods, and fire seasons stretch further into the year. Lightning strikes, which are one of nature's own ignition sources, may also increase as convective storms become more common in a warmer atmosphere. Once a fire begins, dry vegetation and strong winds allow it to travel quickly and relentlessly across the land. The result is wildfires that are more intense, more frequent, and more destructive in many parts of the world. From California to Australia to Siberia, these changes do not mean that every single weather event is caused by climate change. Weather will always vary, and there will still be cold snaps, rainy days, and gentle, mild seasons. What scientists can now do, however, is study how climate change increases the likelihood or intensity of certain events. This field is known as attribution science, and it helps reveal how the background conditions of a warming planet are shaping what the atmosphere delivers. It does not claim that climate change creates weather out of nothing, but that it tilts the odds, making some extremes more probable and more powerful. So what can be done in the face of these shifts? The first step is understanding that not all change is unavoidable. Some warming is already locked in due to past emissions, but future outcomes still depend on the choices made today. Reducing greenhouse gas emissions, transitioning to renewable energy, improving efficiency, protecting forests, and changing how land and food systems are managed can all slow the pace of change. At the same time, adaptation is essential. Communities are redesigning infrastructure to handle heavier rainfall, planting trees to cool cities, and updating building standards to endure stronger storms. Farmers are testing drought-resilient crops, and cities are mapping flood risks and reinforcing coastlines. Individuals too play a role by conserving water, staying safe during extreme heat, and reducing personal carbon footprints. Small actions matter because when repeated across millions of lives, they accumulate like countless droplets forming a storm. The weather remains the weather, unpredictable, beautiful, and full of motion, but the canvas it moves across is changing. Boundaries have shifted, stakes have risen, and humanity is no longer only an observer, but also a participant. The next time the sky darkens unexpectedly, or summer lingers longer than it once did, or rain arrives heavier than expected, remember that this is not only weather unfolding, it is a chapter in the larger story of a planet in transition, still being written by wind, by water, by people, and still very much within reach to shape. And now we have drifted together through winds, and rains floated with clouds, and stood in the quiet hush of falling snow. We have watched lightning carve light through the sky, seen deserts shimmer in silence, and traced the invisible forces guiding weather across the globe. From gentle fog to towering hurricanes, from sunlight physics to the whispers of wind, we have uncovered a little of how this vast living system breathes and moves. Weather is not background noise. It is a conversation between earth, ocean, and sky, a language of temperature, moisture, and motion, written in clouds and spoken in thunder. It shapes landscapes and lives harvests and hardships, calm mornings and restless nights. And despite every satellite model and instrument, it still holds the power to surprise. As you rest now, wherever you are, the atmosphere continues its slow dance. Wind slides over mountain ridges unseen. Raindrops gather patiently on leaves. Somewhere far away, a snowflake is just beginning to take shape. The sky never truly sleeps. It shifts, it flows, and it carries on above us quietly, endlessly. Wherever you are in the world, and whatever quiet moment this reaches you. And thank you for being here, and for slowing down with me through the gentle science of weather. If this journey felt calming, curious, or softly magical, you can support the Sleepy Club by leaving a like or subscribing, so others may also find their way into this quiet space. It truly helps, and it means more than words can say. Now there is nothing left to do, and nowhere you need to go. Let your breathing soften, and your thoughts loosen their grip. Allow them to drift slowly like clouds dissolving into the night sky. Sleep does not need to be chased. It arrives on its own when the mind is ready. May your rest be deep and steady, and may your dreams be gentle and unburdened, like fog settling over a silent field, like morning light after rain.